Okay, so today is the last lesson for thermochemistry for learner outcomes. We spend very little time on this. I expect you to do some reading for this. I'm going to spend the lecture because it's mostly knowledge. You guys have to define activation energy. You have to explain the energy changes during a chemical reaction in terms of endothermic, initial. Everything has to have energy added to it to break bonds. And then everything forms energy as it forms bonds. The label of energy diagrams, and then finally what catalyst is. Now we should know what a grade 9 definition of a catalyst is. A substance that speeds up a reaction but does not take part in that reaction. That is our definition of a grade 9 definition of a catalyst. We're not going to change that. We're just going to talk about how does that affect energy. What does energy do? So 8-minute video to watch here. If the sound doesn't come through, let me know. Actually, I have to turn the sound on and turn my off. Otherwise, I'm going to get a lot of funny things here.
We have atom A reacting with a diatomic molecule BC to form a one diatomic molecule AB and C. According to collision theory, molecules must collide to react. So in this example, atom A must collide with molecule
I forgot to do that. So keep that in mind. And I think I'm done with that video. I'm going to let it go away. There we are. Okay, so activation energy. Talking about collision reaction theory, one that I probably don't stress enough. But collision reaction theories, for a collision to take place, for a reaction to take place, a collision must have taken place with the correct amount of energy, and the collision must happen at the correct orientation. We can't do anything about the orientation of the molecules. We can do something about the energy. One of the best examples that we have is that if I put calcium in water at room temperature, nothing occurs. If I put calcium in hot water, approaching boiling, a very violent reaction occurs because I've managed to get over that activation energy. Now, as I said, orientation, hopefully this will come up. Nope, it's not up on the screen.
Collision theory and reactions 1. In this video, collision theory and reactions 1. In this
Come on, computer. Yes, maybe we won't show this video. What's that?
video, you are going to learn what is necessary for a reaction to take place. For a reaction to take place, the reacting particles must collide. But just because they do collide, it doesn't mean they will react. Now consider a reaction between two diatomic molecules, AA and BB, to give two molecules of AB. This can be represented by the equation these two diatomic molecules can collide in many different orientations, but consider the two orientations here. In orientation 1, the two diatomic molecules A2 and B2 are in the correct orientation to react. In orientation 2, they are not, and so no reaction occurs. Imagine our reaction being that of a ball of yellow plasticine reacting with a ball of red plasticine to give just one ball consisting of the yellow and red plasticine stuck together. If you slowly roll the ball of yellow plasticine towards the ball of red plasticine, they will collide. However, if you pick up the ball of yellow plasticine, the ball of red plasticine will not be stuck to it. No reaction. If you throw the ball of yellow plasticine with the ball of red plasticine, again they will collide. But this time, if you pick up the ball of yellow plasticine, the ball of red plasticine will be stuck to it. There has been a reaction. We call a collision that results in a reaction a fruitful collision. So, for the collision to be fruitful, the reacting particles must collide with sufficient energy.
And at the right orientation. Okay. So, is there anything to copy down on that? So here's just a visual representation using actual two molecules. Carbon monoxide and nitrogen dioxide, they collide at the right orientation, they form an activated complex, and when they separate, now you've got CO2 and nitrogen monoxide. So here they're hitting, so the carbon collides with the oxygen like this. But if the carbon collides with this oxygen. If the carbon collides with the nitrogen, as shown by this, nothing happens because it's the oxygen that has to be ripped off the system. So that's the orientation. We obviously can't do anything about how they collide. We can only do something about how often they collide. Now, this is the thing that we're talking about. Every reaction has to have two more or less instantaneous reactions or changes. You have an endothermic reaction where bonds are broken. If we go back to here, that would be in this activated complex where the bond between the nitrogen and the oxygen are broken. I had to add energy for that to happen. And then the exothermic process where the oxygen attaches itself to the carbon. That gives off energy. Where are we here? So here's another reaction. We've got the reaction of water decomposing into hydrogen and oxygen. I have to add this amount of energy to the system to break the water or to form an activated complex. Here I've got all the bonds broken, but that's the simplification of it. I have to collide the H's and the O's together so the O's hit, the H's hit, and they can break bonds. So now we call it stretch or break. The probable terminology that's better is stretch. So an endothermic process to break the bonds to begin with, and an exothermic process to when those bonds are formed. So in this case, this is an endothermic chemical reaction because the energy required to break the bonds to begin with is greater than the energy required or given off when the bonds are formed. This here, the amount of energy I had to add to break the bonds is our activation energy. Okay, so I had to add energy to break the bonds to begin with, to activate the reaction. If I don't add enough energy, like I add 200 kilojoules per mole, I don't get a reaction. It just sits there and wastes energy, wastes electricity. Now, the overall, just again with our potential energy, the overall reaction is going to give off the difference between the endothermic process and the exothermic process. So the overall reaction is endothermic, even though it has an endothermic stage and an exothermic stage. I think this is basically exactly what I just wrote out or told you, so I'll just let you guys write it down, or how much I made you coffee. So when we talk about an exothermic process like this one on the bottom, the activation energy, the energy that I need to break the bonds originally, is less than the energy that I'm going to get out from when the bonds are being formed. They still have an instant or an exothermic process and an endothermic process, but in that case, the exothermic process gives off more energy than the endo, and the overall reaction is exothermic. So again, the energy threshold to start a reaction is our activation energy. Terminology in the data or in the diploma is activation energy. I have seen threshold energy in different places. So here, however much energy I need to get these bonds to stretch into the activated complex, bonds broken. That is our activation energy. Now, he used the hill example, and I'm going to use the hill example also. You have a hill. You throw a ball at the hill, but you don't have enough energy to get it over the top of the hill. The ball comes back down. That's like not adding enough energy to the system to activate it. If I throw the ball harder and it gets our marble harder over the hill, now it gets to the other side and starts to react on its own. So this from here, yes, that's working. And that didn't work. So the activation energy is from this level spot to the top. Stop doing that. Don't roll the ball with enough energy, gets here, and it's going to come back down. That's an example or a metaphor for the reaction not taking place. Here, we roll to the top of the hill and it rolls back down. Now, this happens to be an exothermic or a version of an exothermic potential energy diagram, but the same would work for a endothermic. It's just the hill on this side would be shorter than it would be on that side. So here's an example of an exothermic process. The activation energy is from where it started to the top of the hill. The overall energy change of the system is from the bottom of the hill to where it stops. Now, if you were asked to read a potential energy diagram, I might include, 200 kilojoules, 400 kilojoules, and negative 80 kilojoules or something. The activation energy would be 200, the difference between the 200 and the 400. The overall energy change is the difference between the 200 and the negative 80, whatever it happens to be, making numbers up there. And here is an endothermic process. The activation energy is from where you started to the top of the hill. The endothermic process is much greater than the exothermic process that we get out here. And that's why we have the endothermic reaction and endothermic overall system. All right, let's see if I can get this catalyst thing to work without blowing my feet.
Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 44. It's on catalysts. Catalysts can speed up a reaction, but they're not consumed in the reaction. What are the great...
I think this part of the technology I'd be able to do because I've had it for so long.
Greatest chemistry demonstrations is elephant toothpaste. And I'm going to put a link right here to a video. This is from Brian Swarthout, a friend of mine, and his son Sam is doing the elephant toothpaste demonstration. Essentially, you add a catalyst to it, and then you have this reaction go really, really quickly. And so please give that a watch. Brian makes some wonderful videos in chemistry and physics. I'll put a link to some of his stuff down below. But how do catalysts work? Well, essentially, they speed up a reaction. Some catalysts will actually slow down reactions, but in general, they're going to speed it up by lowering the activation energy, the amount of energy we have to put in a system before we can stress those bonds, break them, and form new bonds. And so it has to go through this transition state, but a catalyst can stabilize that transition state, and therefore it can lower the activation energy and it can speed that reaction up. Now, some catalysts will actually add new intermediates. In other words, they're going to add new steps in this overall reaction mechanism. And so if you look at the energy profile of a reaction, remember we've got reactants on one side and products on the other. This would be an exothermic or an exergonic reaction. And so essentially we've got reactants, we've got products, but if we want to move between the two, we have to add a little bit of stress to those bonds. In other words, we have to achieve this transitional state. Eventually we can break those bonds and we can form new bonds. And so let me show you a catalyst at work. This is catalase, which is an enzyme found in almost all living cells. So what I'm doing is adding a little bit of hydrogen peroxide to a bag that's got yeast in it. You can try this at home. Shake it up a little bit, and you can see I'm producing a huge amount of oxygen gas right there. And so hydrogen peroxide would do this on its own, but if we add an enzyme to it, we can speed that whole process along. So how does it do that? If we look at the reactants on the left, that's going to be hydrogen peroxide, and the water and oxygen on the right, we see that we have to get through a large activation energy. And so what does catalase do? Well, scientists think there's a heme group in the middle of it. And that means just it's a number of atoms, but it's got iron right in the middle. And what that iron's acting to do is to pull one of those oxygens away. So it's stressing that bond on the hydrogen peroxide, is stabilizing this transition state. So it's more likely to fall into that just water and oxygen. Again, it's going to release energy. But if we look at the energy here, and if we look at the energy here, the net amount of energy that we're getting out is going to be the same. That catalyst is just acting to lower the activation energy. Now, sometimes it works by creating new intermediates, new steps in the reaction. And so in this elephant toothpaste experiment, we're taking concentrated hydrogen peroxide and soap, and then we're actually adding potassium iodide to that, and that's simply going to act as a catalyst. Now, what they're doing, that iodine is going to grab one of the oxygens. So it's going to make this intermediate, which will then bond with the other hydrogen peroxide, and that's going to create some water and oxygen. And so we're really breaking a one-step reaction into two steps, and then we've got a new intermediate here. Well, what does that look like in an energy profile? This would be our original energy profile. We've got reactants on one side, products on the other. But if we look at this two-step process, what we're doing is we're actually lowering the overall activation energy by doing two steps. In the first step, we're freeing up that oxygen, then we're bonding it to the other hydrogen peroxide to make water. And so we've lowered the overall activation energy of that reaction. And so did you learn to translate energy profiles? That's what this is right here. Particulate representations, and even symbolic representations for chemical reactions with and without a catalyst. I hope you did, and I hope that was helpful.
So, most importantly with the catalyst, we know a catalyst is something that speeds up a reaction. That's something we learned in grade 9, grade 10 science. Without changing the reaction, the reactants or the products. So in the H2O2, I still started with H2O2. I ended up with water and oxygen at the end. By adding those two different catalysts, I got different stages to do it. The way they sped up the reaction was lowering the activation energy, lowering the amount of energy that needed to be added to the system to get those intermediate products to occur. Okay. Here's just an example of how much it can happen. If you create, this is basically one reaction. The cis and the trans mean how they're arranged. It's not worried about it. 260 kilojoules of energy per mole without a catalyst, without adding iodine. Drops it to less than half with the addition of iodine. So that reaction happens at a lower temperature, happens quicker if you keep it at the same temperature. Okay, why would you want to have a reaction if you're a technologist? Why would you want to have a reaction at a lower temperature? Yes? Okay. That would be one. The other one that I think about, and I'm probably thinking about, is the lower the temperature, less energy I have to add in, less money I have to spend to get that thing going. Catalysts tend to be reusable, okay? Because they can be, in technological concepts, they tend to be separated out. You can reuse them constantly. Saves money. If I don't have to do it at a high temperature, it's going to save money. So that's one of the reasons why people have looked for catalysts for different reactions for a very, very long time. So graphically, you have a particular, this is our cis and trans butane, I should say. You can see the difference. The activation energy here is huge compared to the activation energy here. The big thing out of this, notice what the overall energy change of this system is. It's still this. Darn it. Where's that? The overall activation, the overall energy change, how much energy we get out of this system, is the same for both reactions. The only thing that's changed is how much energy I had to add to react it to get it to start. And so you have this extra energy pathway that we're going to work with. Now, what you'll see on a diploma exam, and everything shut off, dang it. Can't draw on the board. Well, I guess I'll draw on the board. Okay, so I wanted to do some stuff here, but I'll save it and I'll do it again tomorrow. You have a fair bit of reading to do, and then you have some questions on this. This is the end of our unit. Tomorrow will be a review day where we will go over the unit review package, and then Thursday is your exam. Any questions?